Okay, let us begin our last lecture. It all began with a paper by KANPUR in late 19th century where he introduced set theory. And I mean, he was doing analysis per se, but he introduced the notion of a set in that paper. And ever since then, people have had different opinions. So one of the most famous arguments of KANPUR is the so-called Cantor's diagonal argument. Yeah, because so Cantor's diagonal argument shows that natural numbers have strictly smaller size than the size of real numbers. Naturals and reals were both known to people at that time, but this revelation was so shocking that it divided the group of mathematicians into two. The first group welcomed the idea of formalism, that collection of objects is a set. If I am wearing shoes, then the pair of shoes is a set. The class of students in the set of students in this class, the collection of students in this class is a set. So everybody some people welcome that idea, whereas the distinction between two different kinds of infinities, like natural numbers and real numbers, they are different. So that did not go well with a large group of people. They started calling KANPUR a charlatan. Charlatan means that a person who is just claiming to have some special powers, but they said that he was just a fraud. He's just using sorcery to say certain things which are not really true. They did not like this diagonal argument. I mean, the diagonal argument is essentially an anti-diagonal argument. Because we choose the diagonal and then we say that choose a different digit every time. Okay, so but there was one very prominent mathematician at that time, David Hilbert, who was in favor of Cantor's formalism. And so at the turn of the century, in the year 1900, he posed 23 problems, which are still not completely solved, because Riemann hypothesis, for example, is one of them. And the second problem out of that list of 23 problems was about formalizing mathematics. And like many other people, his hope was that, okay, whatever, like mathematical notation was just being born at that time. So whatever we can verify to be a true statement, we should have a proof of it. So let me quickly recall you that we are going to talk about complete theories. What is the definition of a complete theory? That every sentence is either a logical consequence or its negation is a logical consequence. So he thought that, we should be able to effectively write down enough axioms so that every statement that is true of, let's say, simple arithmetic, natural numbers plus dot less than, that statement we should have a proof of it from the axioms which are given. Now, an English translation of Hilbert's second problem is available. So I am going to just read out the statement. Now, there are very few notations in that particular statement, so it's difficult to make sense of it properly. But this is an English translation because he was German, David Hilbert, and he worked in almost all areas of mathematics which were available at that time. Okay, so he knew everything. That's why he could pose a list of problems that would suffice, that would take over 100 years to solve. When we are engaged in investigating the foundations of a science, we must set up a system of axioms which contains an exact and complete description of the relations subsisting between the elementary ideas of that science. But above all, I wish to designate the following as the most important among the numerous questions which can be asked with regard to the axioms. Yeah, axiomatic system, yeah, something which we do not question, if you remember Munchausen's trilemma from our first lecture, to prove that they are not contradictory. So, to prove that the axioms are not contradictory, what does that mean? That the theory is consistent. Okay, so he asks for consistency. That is, that define a number of logical steps based upon them can never lead to contradictory results. In geometry, the proof of the compatibility of the axioms can be effected by constructing a suitable field of numbers, such that analogous relations between the numbers of this field correspond to the geometrical axioms. On the other hand, a direct method is needed for the proof of the compatibility of the arithmetical axioms. Okay, so arithmetical axioms, so he was mainly focusing on arithmetic because natural numbers are the simplest form of mathematics that we can do. Even Kronecker, who was calling Cantor a charlatan, his quote is also known to us, yeah, that natural numbers are God given, everything else is man created. So Hilbert's second problem was the first step in this direction after Cantor's magical proof of difference between cardinalities of natural numbers and real numbers. Well, whatever Cantor did, those kinds of statements are called self-referential statements, correct? So, because it refers to, so I mean just 1 year after, just a moment, please come here and take it. Okay, so just after 1 year, yeah, in the year 1900, Hilbert posed this list of questions at ICM, and 1 year later, Bertrand Russell came up with his Barber's paradox. Yeah, and Barber's paradox has very similar flavor to what Cantor did. Yeah, a barber can only shave them who don't shave themselves, which can also be translated as the collection of all sets is the collection of all sets which do not contain themselves. Is that a set or not? Yeah, we called it a normal set. And that is also a very similar type of argument, anti-diagonal type of argument. Then later on, people like Zermelo, yeah, they entered the picture and they said that, okay, we are going to resolve this paradox by saying that the collection of all sets is not a set at all. Yeah, so we should write down some axioms, and everything that satisfies those axioms are the only things which are called sets. So there are two important things that are happening here. Yeah, there is one thing called piano arithmetic, and another thing which is Zermelo-Frankel set theory. So in piano arithmetic also we have some set of axioms. Yeah, let us perhaps write them down. What is the language of piano arithmetic? I am going to call it LPA. So that will consist of, I am going to use our commonly used symbol, yeah, instead of using some other F and G. So first one is plus, the second one is dot, and the third one is S, the successor, yeah, the shift or successor, and last one is less than. Okay. Do you remember the axioms for arithmetic? The first one says that 0 is not a successor. This is our first axiom. And how do you write something like that? Negation, there exists W such that SW is equal to 0. Okay, so I think you can translate all these things. Then second one will say that S is injective. Successor function is injective. Then 0 is right identity. Oh, sorry, there should be also one 0. Yeah, 0 is our, otherwise we cannot talk about it. 0 is the right identity for plus. Fourth one, we express sum as sum using successor operator. We have done that in the class, if you remember. So I will write it down. So for all W1, W2, yeah, what is W1 plus S of W2? This is equal to S of W1 plus W2. Very good. And similarly, the fifth axiom says that 0 kills every single element with respect to multiplication. So it says that for all W, W dot 0 is equal to 0. Then sixth axiom says that, well, for all W1, W2, W1 dot the successor of W2 is equal to W1 dot W2 plus W1. Seventh axiom says that 0 is the minimum. 0 is the minimum with respect to less than. Then eighth and ninth axiom says that, well, successor is compatible with, maybe I should write down eighth axiom. Successor is compatible with order relations. So for all W1, W2, W1 is less than the successor of W2. It implies that one of the two things happens. Either W1 is equal to W2 or W1 is less than W2 itself. And ninth axiom says trichotomy. And there is a 10th axiom which I am not going to write down just yet. But this is the so-called induction schema. Okay, so these are the axioms of piano arithmetic. So piano is not the kind of piano you play. You can see the difference in the spelling. Yeah, it's P-E-A-N-O. So it's a surname of a person. Okay. On the other hand, there was Zermelo-Fraenkel set theory. Okay. And Zermelo-Fraenkel set theory, what should be the language of Zermelo-Fraenkel set theory? Loudly. Huh? Union intersection, is that the language? Do any axioms actually use union and intersection? If you remember, what does it use? Belonging to. And there is of course equality, but that's always a part of our meta language. So this is actually same as L-ORD, but I am not going to say this. I am going to use the symbol belonging to, which is a binary relation symbol. So it's just like an order relation. Yeah. Okay. And what are the axioms of Zermelo-Fraenkel set theory? So there is the empty set axiom, then there is axiom of extensionality, then axiom of regularity, foundation, and so on and so forth. I'm not including choice at the moment, but I'm not going to write down that part of that list of axioms. So basically, Zermelo and eventually Frankel, so they came up with this list of axioms to avoid Russell's paradox, which was based on Gödel's which was based on Cantor's anti-diagonal argument. Okay, but almost 30 years later, 1930, John von Neumann met a young logician who was just 24 at that time. Yeah? He met Kurt Godel, and Godel said that whatever is the dream of Hilbert, that cannot be realized. Well, nobody took him very seriously at that time. He was just 24. Yeah? But von Neumann actually believed in him. And a year later, Godel actually published his first paper, which contains the titular first Gödel's incompleteness theorem at the age of 25. Okay? So that was a genius. He was born in Brno, Czech Republic. Yeah, I have lived in that in that city for a long time. Okay, I have to know now how to. I just need to minimize this. Huh? Oh, show desktop. Thank you. See, this is the Ulička Kurta Godela. Ulička it means street in Czech language. Yeah, people still visit this place because Godel was in fact so famous that you can see this picture. Can you recognize? It's Einstein. So, just before the Second World War began, Godel was already famous by then because in 1931 he published his incompleteness theorem. But, and he wasn't Jewish, but still he moved to America with his wife and he went to Princeton. And then eventually when Einstein was offered a job at Princeton, he accepted it just because he would get the opportunity to walk home every single day with Godel. Okay, so Godel is actually a very big name. Even Einstein admired him. So people still visit this place. Yeah? Okay, so let's go back. Okay, now I am, okay, fine. So, yeah, so now we should start talking about what actually happened in that paper. So, Gödel's first incompleteness theorem showed that these two theories are incomplete. Okay, let me state that. GIT1, Gödel's incompleteness theorem 1, it states that the theory of piano arithmetic in appropriate language and the theory of Zermelo-Frankel set theory are incomplete. Once again, let me ask you, what is the meaning of incomplete? There exists a sentence such that it can neither be proved nor be disproved. So there is no proof of that statement from gamma PA. We are only going to focus on gamma PA for most of the parts, the theory of piano arithmetic, and there is no proof of negation of that sentence from gamma PA. Well, how do you prove something like that? So you have to come up with a sentence which does that. Yeah, and there is the genius of Godel, that he came up with that sentence using Cantor's diagonal argument. Okay, so there was no way to get rid of it. Yeah, I mean Zermelo and Frankel were happy that they have bypassed Russell's paradox, but that didn't actually happen in reality. And there are many beautiful consequences of that, which I will read out at the end. So this is the first sentence, and the second one said that gamma PA, sorry, the consistency of the theory of piano arithmetic cannot be proved within gamma PA. Okay, think about this statement for a moment, yeah? What is it trying to say? If the theory is consistent, I mean, Godel eventually proved his completeness theorem. Okay, incompleteness came first during his PhD, and completeness theorems were proved much later. And completeness theorems are all about a proof system. Okay? But the idea of a proof, like a proof is a finite set of sequents, and each sequent is what? Either a logical axiom or a non-logical axiom or modus ponens. Now that idea is still valid over here. Okay? So the notion of finite proof was already around. So basically he showed that if the theory is consistent, if this theory gamma PA, theory of piano arithmetic, is consistent, then its consistency cannot be proved within this same system. Okay, there are many questions around this statement itself. Can you guess one? Normally speaking, consistency is a property of a theory. Yeah, so we talk about it at meta level. Consistency is not a sentence, correct? Consistency is never a sentence in the language. Like this theory is consistent. That's not a sentence in the language. So what is really happening here? It's actually a statement about a theory. But this one says that you cannot prove it by being within the system itself. It's a formal system and it cannot prove its own consistency, if at all it is consistent. And similar statement is also true for this. The theory of, set theory, Zermelo-Frankel set theory, if it is consistent, then you cannot prove its consistency. Sounds weird, right? Why should you expect it to prove its own consistency? But that we will see, like how to construct a sentence which talks about consistency of the given theory. Okay, that was Godel's genius. But before we come to that, we have to understand something. Yeah, this is what we started with. If you remember our first ever lecture, then we started with the question, what is a number, what is a set? And at that time we said that the notion of a set follows from Zermelo-Frankel's axioms. Yeah, we assume them. Now, before I start talking about the details of the proof over here and some consequences, now I want you to pay attention to that part over there. What is LZF? It is a language which consists of a single binary relation symbol. Okay. Now, if at all a model of gamma ZF, the theory of Zermelo-Fraenkel sets. If at all a model exists, if it is consistent, then by completeness theorem, a model must exist. Okay? Let me write this. Yeah? If gamma ZF is consistent and we do not yet know how to prove that, yeah? If gamma ZF is consistent, then it has a model. Okay, but what is a model? What is the data of a model as per our definitions? What should it consist of to begin with? A universe. A universe is what? A non-empty set. Okay. It has a model whose universe is a non-empty set. Say M, say M equal to, this is the model, M comma belonging interpreted in M, and an element of M would be called a set according to ZF set theory. Are you able to understand the problem here? The element of M would be called a set. Yeah, because empty set is in the universe. Then if two sets are there, then the set containing only that pair, that's the pairing axiom. Then if two sets are present, then their cross product is also present, and so on and so forth. These are all the axioms of Zermelo-Fraenkel set theory. So those are the elements of M. But what is the universe? The universe of M is itself a non-empty set. Moreover, when we started discussing logic, what did we say? First of all, for logic there should be an alphabet. Okay? An alphabet consists of a language and a meta language. The language is a set. Okay, now this sounds like a problem which is commonly known as chicken or eggs. What came first? When we are defining logic, then we use sets. And when we are defining set theory, a formal system that we have spent a lot of our time with in this course, that is based on a logic, and that logic itself tells you that you start with a set and then its elements will be called sets. So actually, a simple thing, some simple resolution to this is that this set that we are talking about, the underlying universe of M, that is a set at the meta level. And just like anything else in mathematics, we should assume the existence of that at the meta level as an axiom. Okay, so this one whose universe is a non-empty set, this should be assumed as a thing which you shouldn't question. Because if you question this, then there should be some set theory with respect to which this is a set. and that will be at the meta-meta level. Again, you can question that, and it will lead to an infinite regression. Okay, so once more I want to highlight the difference between mathematical theories and scientific theories in other branches of science, chemistry, physics. Mathematics never claims to make statements which are absolute. All mathematical statements have the form of if this, then that. So, the if part always includes if these axioms are consistent. Well, Godel's incompleteness in fact also tells you that if at all you are consistent, then you cannot prove your own consistency. If I mean some historical remarks about this, that later on, like 6 years after Godel's first incompleteness theorem and second one also, in 1936 or 7, Gentzen, Gentzen's name is also very prominent in the field of logic, because we saw Hilbert style calculus. The other style of calculus in propositional logic as well as predicate logic is called natural deduction system or Gentzen style system. Okay, so he gave a proof system. So Gentzen's name is also very popular. So Gentzen proved that assuming the axioms of Zermelo-Fraenkel set theory, you can prove that Peano arithmetic is consistent. So Zermelo-Fraenkel set theory is much more complicated, right? Because in that set theory, we can define the set of natural numbers. We did that using axiom of infinity. Then we can also discuss the addition operation, multiplication operation, successor. Everything is definable in the language of Zermelo-Fraenkel set theory. So it is a much stronger system. So if you assume that stronger system, then you can actually prove that Peano arithmetic is consistent. Similarly, if you assume that you are given gamma ZF, Zermelo-Fraenkel axioms, plus a sentence like there is an inaccessible cardinal. Okay, it's a statement that you can write down in this language. Some cardinal which cannot be approached by just addition, multiplication and exponentiation operations, the usual operations that we do. We cannot prove its existence in ZF. It's just like axiom of choice or continuum hypothesis. But if you assume that extra axiom, then you can prove that gamma ZF is consistent. So always a slightly stronger system will prove consistency. Gentzen in fact gave a proof of consistency of gamma PA not by remaining within the realm of finitary first order logic, but he went and used transfinite recursion, a transfinite induction until the ordinal epsilon naught. Do you remember epsilon naught? Epsilon naught is the smallest ordinal which is solution of omega to the x is equal to x. So it is omega to the power omega to the power omega to the power omega and then dot dot dot. So he gave an infinite length proof of the consistency of gamma PA. Okay, so what Godel's incompleteness theorem says is that there is no finite length proof which uses the axioms of Peano arithmetic which are written here. So there is no proof of the consistency of Peano arithmetic from these axioms thought of as non-logical axioms and some logical axioms, obvious ones, and modus ponens. There is no finite length proof, but Gentzen provided an infinite length proof. And later on people also found a proof of consistency of gamma PA from gamma ZF. But again, the question remains whether gamma ZF itself is consistent, and that you can prove using something slightly more slightly stronger. Yeah, just assume one extra axiom and then you can prove this. But how far can you go? Yeah, that if I assume an extra sentence like there exists an inaccessible cardinal, then is that system itself, that system of axioms, that theory, is that new theory itself consistent? Well, the answer is, thanks to Gödel's incompleteness theorem. I mean, I haven't written the exact statements yet, yeah? But it says that if you can do arithmetic in that, then you cannot prove your own consistency. So even in that new system, you can do arithmetic, elementary arithmetic, so you cannot prove your own consistency. So you'll need to go a bit higher to prove its consistency. So if you add this one to this list, then you have to go higher to prove this consistency. Now you imagine this situation is very similar to Cantor's original argument. You remember Cantor's original argument was, let us list all the decimal expansions of real numbers between 0 and 1. And if you can list them, then you take the diagonal and you twist it. Yeah, you change the entries on the diagonal. Now that particular sequence never appeared, so therefore then the natural question is, oh, add it to the list. But even if you add it, the same argument works again. Again, if you get the same thing, so this is a never ending process because it's self-referential. It references itself again and again. So therefore, this will never be possible. Now, what people worry about, yeah, I mean, some of you, I hope, will go on to do research in mathematics, and once you start attempting a particular open problem, at that time, can you be sure that this problem is solvable? Nobody really knows that. Yeah? Before you have a solution, you have a proof, you can't really know whether it is solvable. But what if this problem is one of the sentences given by Gödel's first incompleteness theorem, that there cannot exist a proof? What mathematicians try to do is that they try to find a finite length proof of any given sentence in some formal system. But what if this statement can neither be proved nor be disproved from the given axioms, because the axioms are not strong enough to conclude something like that? One such statement which people believe is the twin prime conjecture. Do you know what twin prime conjecture is? That there are infinitely many sets like pairs of primes which are only 2 apart. So something like 3 and 5, 41 and 43. So there are infinitely many such. Now you cannot actually, know for sure whether twin prime conjecture is provable or not. Riemann hypothesis is a big statement. Yeah, whether it is provable or not, nobody knows. Goldbach's conjecture, which states that every even natural number greater than 2 can be written as sum of 2 primes. Is that statement provable or not? See, now that particular statement, yeah, twin prime conjecture, Goldbach's conjectures, they are all about some concrete system. Okay, so twin prime conjecture is about natural numbers which can be expressed in this language right? Okay, so anything that can be expressed in this language is either true or false in natural numbers. Do you agree with that? Because the theory of any structure is complete. So every sentence is either true or false in that structure. So even if twin prime conjecture is true, we may not have a proof of it from these axioms. Now you might say, add new axioms, but again, Godel's incompleteness theorem says that, oh, you might want to add new axioms, but whatever you do, you can never reach what, there will always be a sentence which says that this can't be done. Okay, so this is a very interesting situation, and many people were afraid, like mathematicians were in general very much disappointed as well as scared after looking at these Godel's theorems, because they say that there is a limit to what a human can do with formal systems. Yeah, however, like in past 50 years, the way of looking at Godel's incompleteness theorems had changed considerably. Now people look at it positively. So why is that so? Because suppose you can prove that a given sentence is true, but it's neither provable nor disprovable. Then you can add it to your own language. If you find that is interesting, then you add it to your own language, your own list of axioms, and then you try to proceed. So mathematics will always remain interesting. You can always find new consequences of statements that you like. So for example, in gamma ZF, the sentence, this statement is says that it is incomplete. For gamma ZF, I am sure all of you know what is that sentence which can neither be proved nor be disproved. The axiom of choice. Then the continuum hypothesis. Yeah, you know at least two statements which can neither be proved nor be disproved. But has that stopped mathematicians from adding them to your list of axioms? I mean, the name itself says axiom of choice. We have been proving Godel's completeness and completeness theorem and compactness theorem, everything using the axiom of choice. The proof that axiom of choice is independent of the rest of the axioms of Zermelo-Fraenkel set theory, that was given by Paul Cohen in 1963, much later, okay, 30 years later. The original sentence of Godel, which can neither be proved nor be disproved, is different. But axiom of choice is a widely accepted statement. Now there are many people who do lot of research in number theory and in complex analysis by assuming Riemann hypothesis. They say that if Riemann hypothesis is true, then this happens. So people spend their lives. Another such conjecture is, for example, people don't know whether e to the pi is rational or not. Yeah, nobody knows that. These are so easy to state problems, and now because thanks to Godel's incompleteness, will forever be in dilemma whether this statement can actually be proven or not. So Roger Penrose, yeah, a name very popular, he is a Nobel Prize winner, mathematician, physicist, and also a philosopher. Like at a very late age, now he is very old now, he has crossed 90, but he has now tried to understand something about Gödel's incompleteness theorem and consciousness, human consciousness. Yeah, I mean, what is it that separates humans from machines? So before I read out his quote, yeah, I want to say something here, that as a corollary, yeah, Godel also proves that gamma PA and gamma ZF are undecidable, which means there is no algorithm which can check whether a given sentence follows from the given list of axioms. Which means whether there is a proof, finite proof from the given list of axioms. So there is no computer program which can check this. Okay, so now everything thanks to Cantor's anti-diagonal argument, which is a self-referential statement. Now let me read out the quote by Roger Penrose. When I learnt what it really said, that there are things that if you had a computational way of proving things in mathematics, then you could always transcend them. Transcend is go beyond. Yeah, transfinite. Transcend is also something like that. And transcend is usually a word which is used in spirituality. Right? So, then you could always transcend them, because it showed whatever computational rules you had to prove things, knowing that there are that these actually did prove things that enabled you to transcend the capabilities of that machine. Yeah, because this statement says that you are exceeding the capabilities of any machine that you can think of. And I found this really remarkable. Whatever conscious understanding is, it is not a computer. Okay, I mean, a computer can only do certain things. You can feed it some rules, you can feed some input, and then it can give you some output. So people also take this as Gödel's incompleteness in a positive way now, that it says that human consciousness can never be modeled by a machine, because whatever a computer can do, it's only finitary, and finitary things have limitations. Any questions? Anything to say at this point? Because after this we'll go into little bits of the details of the proof. I know it's a lot to take in. Okay, let's do some serious mathematics then. Yeah, so we have to understand what is that Gödel's function, Gödel's sentence, which says that this is incomplete, the sentence which can neither be proved nor be disproved, and how Cantor's diagonal argument was used in that, and we have to also understand this undecidability. Okay, so let me start with the definition. I feel like these things students find really interesting, the things I am about to present now. So that is the concept of recursive functions. Okay, so here I am going to talk about omega, or I mean natural numbers. So I am just going to say that the set of recursive functions is the smallest class of finitary functions f from n to the n to n, such that first one, that projections, yeah, so pi I from n to the n to n is recursive. Second one, addition from natural numbers square, addition and multiplication are recursive. Third one, the identity function, the characteristic function of the less equal set from natural numbers to natural n square to n is recursive. Do you understand this chi less equal? So it is the characteristic function of less equal. So 2 comma 3 will be mapped to 1, but 3 comma 2 will be mapped to 0. Composition of recursive functions is recursive. And fifth one, if f is a function from n to the power n cross n to n satisfies the following. What is that following? That if, and sorry, for all a bar in n, there exists a b such that f a bar b is equal to 0. Yeah, this is the property. Then there is, then the function g from n to the power n to n defined by g of a bar to be the minimum such b, minimum such x in n, such that f of a bar comma b is equal to 0 is recursive. Oh, sorry, if this is recursive, I should add that f is recursive and satisfies the following property, then this is also recursive. Okay, so this is a commonsensical definition. Okay, projections are recursive. Yeah, then addition, multiplication, these are our normal things, normal functions that we would like to deal with. Composition, order relation, and this is like the using the well ordering property of natural numbers. Yeah, that you can always choose for each tuple, you can choose the least one. So this is also recursive, and it is the smallest class obtained by these rules. There is only one closure rule here, which is composition. And no, sorry, these are the two closure rules. Closure is as in, like if you know something belongs to that class, then you know something else also belongs to that class. Yeah, these are absolute things. They don't change. They are like our induction base cases, and these are your inductive cases. So these are called recursive functions. Okay. So this was originally defined by Godel himself. Then a few years later, in 1935, if I remember correctly, Alonzo Church, he was also developing something which we now call lambda calculus. That's a branch of computer science. And he was trying to do something which is computable. So at that time, computers were not machines. Computers were people, and especially women. Yeah, women used to sit in an office in front of some box, and they used to do long calculations. There was no automated process back then. So whatever notion he had, using his idea of computable, so there came in the statement that we now call the Church-Turing thesis. You must have heard master's thesis, PhD thesis, but this thesis is a thought. It's a thought that you have had for a long time. You have thought about its pros and cons, and yeah, thesis is actually a thought that you have mulled over for several months, years also. So Church-Turing thesis is the name that we know right now, that computable is same as recursive. Okay, so let me write down three different things. So first one was of course Godel, and he came up with recursion theory. Recursion theory is the study of recursive functions that I just defined. Then second one was Alonzo Church, and he came up with lambda calculus. And eventually, during Second World War, the Allies had a great help from a very powerful brain, that is the father of computer science, Alan Turing. So Turing came up with the concept of a Turing machine, and that is where the actual computability theory originated. So actually now we know, yeah, these three great minds, they came up with three different theories, but they are all equivalent. Okay. So in lambda calculus there is something called lambda abstraction operation. In computability theory also there is something. And recursion theory, we have this mu recursion. Yeah, this min of x, so this is usually written as mu of x of, sorry, this was x. F a bar b, a bar x is equal to 0. This is usually written like this, the mu recursion. So these all things are actually the same. These three different theories which originated at the gap of like within 10 to 15 years, they are essentially the same. And therefore Church-Turing thesis, which was a philosophical statement at that time, that is also true. Yeah, because now all these theories are well developed, and this shows that whatever three people can do, yeah, three great minds can do, that is the truth. Yeah, a computer cannot go beyond any of this. computer cannot transcend the capabilities of any of these three equivalent theories. Whatever is a computable function, only that thing you can compute. If it is not computable, it is also undecidable, it is also not recursive, everything is banned. Okay? So there are capabilities for a machine and they are given by all these three theories at the same time. Okay, so recursion theory and a representation theorem for recursive functions, that is one of the most important components of Gödel's incompleteness theorem proof. Okay, a representation theorem, if you remember Stone's representation theorem, yeah, something of that sort. Okay, so this was the first ingredient. The second ingredient, and which is also a crucial ingredient, that is called Gödel numbering or Gödel coding. Now this is based on a very simple idea that n square is in bijection with n. So therefore, pairs of natural numbers can be encoded in such a way that is just one natural number. Well, why not repeat this idea? If you can do pairs, then you can do triples. If you can do triples, then you can do any finite length sequence. If you can do any finite length sequence, then why not do all finite length sequences at the same time? Without using countable axiom of choice, you can actually achieve that. So what Gödel did was he used a very simple pairing function. So pair of xy is defined to be x plus y plus 1 divided by 2 and plus x. So this pairing function is bijective on natural numbers, n square to n obviously, and recursive. Yeah, this is the particular function that he used. Then Gödel also defined something called the beta star function and the beta function. Gödel's beta functions are popular. So beta star function, what it does, it takes a triple of natural numbers and it gives you the remainder when A is divided by I plus 1 times B. So this beta star function, this is injective from n cube to n, yeah, from n cube to n, and recursive. And finally, he defined this beta function which is only on a comma I, which combines both these statements, and what he does is he takes a beta star of pair inverse of a comma I. Okay, so pair is a function from n square to n, its inverse is going to be a function from n to n square, so pair inverse will give me 2 elements and comma I. Yeah, that's what this is. So Gödel's beta function is the key to code any finite sequence into a single number. Okay, now let us see, I am going to use a slightly different approach. Gödel used these functions, but I am going to use a slightly different approach for coding things. So all of you remember that countable union of countable sets is countable. Yeah, and we are going to look at something very specific, that the set of finite subsets of natural numbers is also countable, and we will do that. Yeah, so therefore we have also seen that even in propositional logic, if your language is finite or countably infinite, then the set of all formulas is SL is also countably infinite. Yeah, we have done that. And the same idea will also work for predicate logic. So we have to use our alphabet. So what is alphabet for logic? Well, this is meta language plus language. In meta language we had quantifiers, we had connectives. How many of them? Just two, negation, conjunction. Then we also had one quantifier. How many? Just one. Yeah, let me write them down. There exist. Then we had an infinite set of variables. Yes, we said that every time we need one variable, we have a variable available. So variables, they are x1, x2, xn, a countably infinite set of variables. And also, what else did we have? Equality, very good. And in the language we had three different parts. One was relation symbols, then function symbols and constant symbols. Okay, so this is our beginning. Yeah, and also there are parentheses, it doesn't matter. My point is that if your language happens to be countable, then this alphabet is also countable. So Godel numbering is a way of assigning a number. So each xi will go to twice the n. So this will get mapped to 2, this will get mapped to 4, this will get mapped to 6 and so on. Okay. Then this will, let's say, this will get mapped to 0, this will get mapped to 1, this will get mapped to 2, this will, 3, this will get mapped to 5. Then all relation symbols, function symbols and constant symbols, assume that you are already giving some injective functions to natural numbers because they are countable. So there is a fixed injective function, and assume that those injective functions are also recursive. So they will also be mapped. So these things together, they will be mapped to odds after 5. You understand this way of numbering things? Or maybe I have missed out parentheses, you can add them and then you say 5 and 7 are taken for parentheses and you do this later. Okay, now let us try to do it for a particular language which is LPA. LPA consisted of plus dot s 0 and less than. Okay, so maybe I will map this to 7, 9, 11, 13 and 15. I am choosing a function and I am assuming that it is recursive. Now let us write down one particular term. What is a term? Term is either a constant symbol. Well, what is that constant symbol? It is, so let us say our term is 0, it can be 0, it can be xn, it can be some function symbol applied to something, so maybe it will be xn plus 0, anything that you like. Okay. Now we can associate to this any term one unique natural number. How to do that? So what you do is you take the Godel number of 0. This is the Godel number of 0. This hat notation denotes the Godel number. What is the Godel number of 0 in this case? 13. Okay, good. So what is the Godel number of xn? What is the Godel number of xn plus 0 sequentially? Sorry, I shouldn't say this. I'm making a mistake here. I should say Godel number of xn and Godel number of xn, Godel number of plus and Godel number of 0. Okay, I'm just writing these things down, but I haven't told you what to do. We simply order prime numbers. First prime, second prime, third prime, we can do that. Yeah? And I actually assign the number 2 to the power Godel number of 0. Then 2 to the power Godel number of xn, 2 to the power Godel number of xn, 3 to the power Godel number of plus and 5 to the power Godel number of 0. We have seen this idea. Okay? So, this way you are assigning to each single term one number, and from that number you can actually determine, this is an injective function. Yeah, because if terms are different, then their syntactic forms will be different and therefore you are mapping it to something different. And by doing the prime factorization of the number obtained, and if you know the original Godel numbering of the alphabet, then you can recover the formula. So the formula is, the term itself is a number. Not all natural numbers correspond to terms, but those which do, you can recover the original term from that. You can do the same thing with formulas, because formulas are also finite list of symbols. So you can do the same thing. So every formula will have its Godel number, every term will have its Godel number, everything will have a Godel number, and they will all be different. Okay, so Godel numbering is an injective function from the set of formulas, set of terms, union the set of formulas to natural numbers. Yeah, so this is the injective function, this is the blank, the hat blank. And for this, Godel actually used this beta function. Yeah, I am showing you something much simpler here using primes. Okay, once you understand this, now let us go one step forward. If you remember proof systems, so what do proof systems consist of? Axioms, yes. Proof systems have two different parts. One is logical axioms and then you have rules of deduction. Okay. So, logical axioms themselves are sentences or formulas. I mean, if you wish, they are formulas, so they will have their own Godel numbering. Similarly, I mean, if you add this turnstile symbol into your language and some way to add that this particular formula is over and now you are starting with a second sentence, second line of proof, formal proof, then you have also encoded every single sequent as one number. Understood? Logical axioms have their own Godel numberings because they are sentences. Then all the non-logical axioms, so in our case we are talking about piano arithmetic. So piano arithmetic will also have its own Godel, like every single sequence in that piano arithmetic will also have its own Godel numbering. So in total, every single logical axiom, every single non-logical axiom or even modus ponens, you can assign a Godel numbering. And using those Godel numbers, now every finite length proof is also getting its own Gödel number. Yes? Finite length proof would be a number because it will be a sequence of numbers which you can encode again, and then you get one single number. Whenever you can get a sequence, finite sequence, then it is again a number. Yeah, that's what Gödel's beta function does. So every proof will also get a number. Yeah, so I'm just going to write down every proof also gets a Gödel number. Okay. Now we are very close to saying what we want to say. Okay. Now the formula that I want to talk about, and here we are assuming like the proof of Gödel's theorem proceeds via saying that if you assume that the language is recursively enumerable, yeah, then these functions, Gödel numbering function is also recursive. Yeah, so we are talking about recursive functions all the time. Okay, now is proof of gamma sub PA. This is a binary relation and it takes two arguments, A and B, and when is it true? So this is true if and only if, I mean maybe not this, if and only if A is the Gödel number of a proof of the formula of the sentence, let's say, with Gödel number B. Okay. So what we are saying, something is a proof of a form sentence. There might be multiple proofs, but we are writing down it as a binary relation on natural numbers. Yeah, Gödel numbering allows us to compress data further and further and further and further, so that now we are also saying something like this. So 355 numbered proof. Yeah, I mean the proof whose number is 355 is actually a proof, which means its last sequent, the right hand side of the last sequence is sentence phi, whose Gödel numbering is 19. We can write that. Okay. Now we are very close to stating the Gödel's sentence, which can neither be proved nor be disproved. Once this is proof of comes into play, it's very easy. Okay. So the first sentence is this. That sentence is also called beta gamma. For all W, negation is proof of gamma PA. W beta gamma PA and complete. This is our Gödel's sentence. Okay, it takes some time to grasp what it's trying to really say. It says that this statement does not have a formal proof. See, just read the second half part. second half after this if and only if, it says that for all W, W is not, yeah, so there is no proof of the Godel number, I mean the sentence, the Godel number of the sentence of beta gamma Pa itself. And beta gamma Pa is true if and only if it doesn't have a proof. You can write this down. Yeah, this is a sentence in our language. Yeah, I haven't given you full details, but simply this sentence says that this sentence does not have a finite proof. Cantor's original argument. Because if it had a proof, then you can prove it doesn't have a proof. If this statement were true, yeah, what does it say? Yeah, I mean, let me write it down informally. This statement does not have a proof. If this statement is true, then it must have a proof, which means it's contradictory. That means our gamma Pa is itself not consistent. We don't want that. Yeah, because if we say this statement is true, then we can find a proof. So therefore, we are contradicting the given statement itself. So that shouldn't be true, right? So, and moreover, I mean, this is the main part, that the theory gamma Pa can prove the Godel sentence for gamma Pa. Yeah. So this is what Godel showed. Okay. So therefore, beta gamma Pa is the statement which cannot have a proof. If it is true, then it leads to a contradiction. So the only other option is that, if it is false, I'm making a mistake. If this statement that beta gamma Pa doesn't have a proof is false, then what will happen? Then there is a proof, and that is contradictory. So this statement cannot be false. So it must be true, but if it is true, then it cannot have a proof. You understand? This is the statement which is self-referential, and it's similar to Cantor's original argument, right? One last thing, yeah, I will quickly tell you what is, I'm well over time, but I will still say. The consistency of a theory gamma can also be written as a sentence. I promised you that. Yeah, that I will tell you a sentence which does that. So it says that there exists a W such that is provable W, is provable gamma is simply there exists an A such that is proof of AB, right? Is provable, that's easy to understand. W, and there exists a W dash such that W dash is the Godel number of negation W and is provable gamma W dash. Okay. Look at this sentence, it says that there is, this actually says consistency. sorry, this talks about inconsistency, so I should put a negation, yeah, in the beginning. So it says that there is no statement which is provable and its negation is also provable. And that we could write in a single formula thanks to Godel numbering. This statement says consistency, and Gödel's second theorem actually shows this, that suppose gamma is recursive. Yeah, I will define recursive in a moment, and gamma can prove gamma PA. Yeah, its language is sufficiently strong to do elementary arithmetic. If gamma is consistent, then gamma doesn't prove its own consistency. Then there is no proof of its consistency from gamma. So this is the actual second theorem. And the thing that I did not mention is what is recursive. Recursive set is, just write down these definitions. So recursively enumerable set. This is projection of a recursive set, and the theorem is that a set, when do you call a set recursive? If its characteristic function is recursive. Yeah? Because we can always switch between sets and functions. Characteristic function is recursive. So this is projection of a recursive set. You understand projections? There exist quantifier. So you have a set in, let's say, n dimension, you project it onto n minus 1 dimensions by saying there exists a last component. There exists a W such that it happens. And a set is recursive if and only if set X is recursive if and only if both X and complement of X, yeah, n minus X are recursively enumerable. This recursive and computability, they are same, so therefore this is a very important topic in computer science as well as logic. People spend their lives determining decidability of certain theories, whether there is an algorithm. Because if there is an algorithm to do something, then, well, we want faster mobiles and computers, yeah? Everything depends on these decidability proofs. So therefore, lots of people spend time on this. So, the first statement, GIT1, says that no recursively axiomatizable theory containing the theory of piano arithmetic is complete. And I have already explained the consequences of that. And this is our second statement, that anything in which you can do piano arithmetic, it cannot prove its own consistency. So there are always going to be limitations. Now people don't really know whether Gödel's incompleteness theorems really answered Hilbert's second problem in the negative. Because what Gödel showed is that by remaining within the same formal system, you cannot prove its own consistency, you cannot prove it's complete. But that doesn't stop us from finding out another proof system which can prove everything that is true. Another set of axioms which can prove everything that is true in natural numbers. But at the moment, no human is smart enough to figure out what that other system could be. Let's stop here. Thank you.